This material should prove to be mostly a review for you guys, but just in case, I wanted to go over it again, make it available to you. I know it's been a long time, it seems like, since we went over it. So, igneous environments. You can follow along in the PDF file online, but I have all those slides in here in the video also. So, let me see if I can get everything going, right? Yep, here we go. There we are. So, magma cooling rates and texture. We look at this. This is a nice little basalt, cooling very quickly. It's mafic, but what we're getting at first is the fact that it's extrusive, which means it cools quickly, which means it's fine grained. When we look at something coarse grained where we can see the big crystals in it, it's intrusive. It cools slowly beneath the surface of the earth. Well, my slides are jumping around on me a little bit. I apologize for that. So I want you to be sure that you can figure out this igneous rock chart. Make sure you got it in your head because it's pretty important, the words that connect the minerals to the plate tectonics. So let's go through this one at a time. I'm going to say them, but you should pause this video for a second and see if you can answer them also. Okay, let's take it from the top. Felsic and intrusive. This one where my little hand is, that's our granite. You might find that at Yosemite National Park. Intrusive intermediate diorite. Dies out right down underneath the Andes or other subduction zones. Felsic on the continents, intermediate subduction zones. Mafic, it's going to be on the ocean bottoms. Intrusive would be big crystals. That's our gabbro. Extrusive, felsic, that's in a volcano in the interior of a continent such as Yellowstone, forms the rock rhyolite. Intermediate, again, subduction zones. Extrusive, a volcano like at the Andes or Mount St. Helens. Mafic, extrusive, would be out in the middle of the ocean bottoms, such as at Hawaii. We get mafic. Extrusive is a basalt. Some pretty pictures: granite, rhyolite, diorite, andesite, gabbro, and basalt. But don't forget a couple other important igneous rocks. Obsidian, which is the glassy one, and pumice, that's lighter than water, the one that floats. Foamy is the way I've described it sometimes. So, how do rocks melt? Rocks melt because the center of the earth is a lot hotter than it is up on the surface. So as you go down deep within the earth, the temperature increases, but so does the pressure. The temperature increases because the earth hasn't cooled off all the way through. One of the reasons, even though it's really old, it hasn't cooled off already is because it's continually warmed from the inside by naturally occurring radioactivity. So let's take a look at these diagrams. First thing, at point A, we're up near the surface, so the pressure is low, the temperature is low. If we increase the temperature, maybe because of a magmatic intrusion or something else going on, something causes it to get hot, but it's not very deep, so we're still under fairly low near surface pressures, but high temperatures. This line tells us we're on the liquid side. It melts. But if we go with the same temperature down deeper, higher pressure, we're on the solid side. So we can get, for the same temperature, either a liquid or a solid, depending on the combination of temperature and pressure, not just one of those two. Same sort of thing here, is just showing you that same idea that as you bury it, it stays solid at a higher temperature, but if it's up near the surface, it's a liquid. Now, one that I often put on test is this figure, because this figure has two lines. Notice the wet line is dashed, and the solid line is dry. What we're getting at there is if the rock we start with is dry, we use this line. If the rock we start with is wet, we use this line. So at point E, if we start with a wet rock, like at a subduction zone, and bury it so it's under high pressure and high temperature, it's going to melt. It's going to become a liquid. But if we start with a dry rock, doesn't have much water in it, and bury it and heat it to the same temperature and pressure, it's going to stay solid if we start with a dry. So this is particularly important at subduction zones because those rocks coming off the ocean bottom are wet. This picture we've talked about like being the vomit stuck in the neck of someone who threw up, in this case the volcano. The old volcano went way up higher and it's eroded down, but this last little vomit that came out and solidified inside the volcano is a little bit more resistant to erosion, so that as the rest of the volcano wore down, this part was left sticking up. This is a shiprock in New Mexico. We see the same thing, this picture of me in Kenya. You can see the same volcanic vomit sticking up here that was left behind as the rest of the much taller volcano eroded down. So, hope this gives you some ideas about the, well, I can't get this thing to show up completely. Well, the key ideas in terms of this, we're mainly looking at the rocks as a way of telling the story of the Earth using the words that connect the small scale letters of the mineralogy to the big scale things of plate tectonics.